Hi Year 8, welcome to the next video that will help you revise chemistry for your summer assessment 2. In this video we'll be looking at some types of chemical reaction, very quick visit through the different types of chemical reaction that take place, the changes that take place in chemical reactions, which are really vital to a chemist's work. It'll also be helpful to be able to predict reactions and to recognize patterns in the types of reactions that key elements and compounds undergo. By grouping reactions and spotting general features, chemists can be more precise in their predictions. So the different types of chemical reaction, if I can just review them with you. The one that we can all seem to relate to is combustion. Now, this symbol over here tells us that something is combustible. Now, the interesting thing is that the word flammable also has the same meaning as inflammable. So, little fact there, but you can see that there is it very clearly shows that something is burning very easily in air. And fires do need oxygen. Oxygen reacts with a substance. Energy is transferred from the store of chemical energy that's inside the combustible material, mainly as radiation. It warms around the surroundings and warms the air around it. So that's the process of combustion, which we commonly refer to as burning. So the reaction that you see in a Bunsen burner is pretty much, and this also links to the stoves that you have at home, the gas cookers. Methane, which is a hydrocarbon molecule, it's C with 4 H's connected to it. So methane, and you actually need 2 molecules of oxygen. You need 4 atoms of oxygen in total, oxygen gas, because 2 actually are in a single molecule of carbon dioxide. You see that there's the C there, so the C's are balanced. And you also need water as a product, so you need 2 molecules of water because that's 2 O's, one from one of these diatomic molecules, and then you've got the 4 H's, which divided by 2 is equal to 2. So Bunsen burners, stoves at home, they use methane as a fuel. When we turn the gas up or when we turn the gas down, what we're actually doing is we are controlling the amount of air, the amount of oxygen that's mixed with the methane. So as you control your gas at home, you're increasing the amount of gas that's going through, but you're also increasing the amount of air that's mixed with it as well. And this particularly works well with Bunsen burners as well. When you have an air hole that's open, more oxygen can reach that fuel and the flame is at its hottest, and that's what we associate with a blue flame. Now, here's a setup that we should be familiar with, and this is a setup that tests for that carbon dioxide and that water. So effectively, if we have the products of combustion, this is a fuel that's set on light. This is the suction pump. I talked to you about this before. This transfers through, it sucks through all of the gaseous products that you have from this burning fuel, and the first container, this is actually called a U-tube, believe it or not, so I'm describing YouTube on YouTube, which is quite ironic. The first container is a cold container because the gaseous water vapor, which is a gas, goes through here, and below 100 degrees centigrade it will condense to form liquid. So once it forms a liquid inside this container, we can then open up the container, we can then do some chemical tests on it, and the ice surrounding this keeps this nice and cold. The other gas that forms is carbon dioxide, and that does not solidify, it does not liquefy. It keeps going through this suction pump, so the suction pump forces the gases, the products through, and here's lime water. We've met lime water in a previous video. The lime water will turn from colourless to cloudy white, milky white colour, and that will reinforce and that's our chemical test for carbon dioxide. So this experiment shows the way to collect the products of combustion. The gases are pulled through the apparatus by a suction pump, and due to the ice bath around this middle tube, this U-tube, the water vapor produced will condense inside, and the carbon dioxide bubbles through the lime water turns from colourless to milky. So these are the two products. We don't see any other products. We don't expect, rather, any other products when we're supplying lots and lots of air, lots of oxygen to the actual burning fuel. The water here in this example does have a G because the temperature reached when methane burns is above 100 degrees centigrade. But some people could actually also justifiably say that this should be an L because state symbols tend to be given in the state that the chemical is in at room temperature. So both seem to be acceptable for different reasons. So that's combustion. The second type of reaction is a reaction that I remember, on UAE National Day. So we actually had some chemicals with the different colours, and this was copper carbonate. So copper carbonate, when you heat it, it breaks down. So it's called a thermal decomposition. The copper carbonate itself breaks down to two substances. One is copper oxide, which is black, and the other one is carbon dioxide, which comes off as part of the carbonate. So there's no other reactant here. It reacts to form copper oxide plus carbon dioxide. It's a nice chemical equation to cover because the Cu is balanced, and one of the O's is here, and the other two O's is there, and you've got the C. So it's a very nice example of a balanced chemical equation, and the state symbols are there: solid, solid, and gas. So again, the product of this reaction could be tested with lime water if you really wanted to. You could channel that through. You could put another test tube. You could put a delivery tube rather with a bung and just heat it, and then have an open test tube with some lime water in, and you will test that lime water. And we've done that exercise already. So that is thermal decomposition. The next one is one that does confuse a few people because of the term reduction. So people tend to understand what oxidation is. Oxidation is a gain of oxidation is a gain of oxygen, and reduction is a loss of oxygen. Now, you can also talk about oxidation and reduction when we're talking about electrons. Reduction is gain of electrons, loss of electrons is oxidation. But this, just for key stage 3, this is all you need to know. So the oxidation occurs when a substance reacts with oxygen. So combustion, which we've just covered over here, combustion is also an example of oxidation, but there are others. We've studied magnesium heated in air to form magnesium oxide. It's a direct synthesis. We've got an example of another metal, which is zinc over here. So zinc plus oxygen, it actually forms zinc oxide. It's a 1-to-1 ratio. So because oxygen is a diatomic molecule, you have to have two zincs because you then have two ZnOs to balance it out. And zinc oxide is actually a solid. So metals, typically, when they can react with oxygens when heated to form metal oxides, as in this example. Now, the opposite of oxidation is called reduction, and that's where you actually have a removal of oxygen. So here's the substance, iron oxide, and you can see that the iron oxide is iron with the oxygen bound to it, and after the reaction you see that the iron is on its own. So the iron oxide is reduced, okay? Now the carbon over here gains oxygen, so you can say that the carbon is oxidized and the iron oxide is reduced. Just do the quick numbers over here. So that's 2 times 2, that's 4 lots of Fe. You can see that that is on its own, that's 4 Fe. 3 2s is 6, so you would expect to have 6 oxygens. 3 times 2 is 6, so you do have 6 oxygens on this side, and the 3 Cs help make up the carbon dioxide because each of the molecules is a C bound with 2 oxygens. So you can see that there are certain cases where you have reduction and oxidation taking place at the same time. This is really, really useful when you have a metal that is bound with oxygen, and you dig that up from the ground, so you quarry it from the ground, and you want to try and extract that metal from that ore. You would then think about doing a reduction oxidation, which is sometimes shortened to the term redox, and a common way of extracting the ore metal that you desire is by heating with carbon, and this is the one that we actually showed you in class. And I did carbon with copper oxide, and we reduced the carbon. We use the carbon to reduce the copper oxide to form copper. So it's a very similar reaction to the one that you can actually see on the screen. If that is the case, and it's the case over here as well, we can actually say that carbon is oxidized, but we can also classify the carbon as being a reducing agent because it encourages the reduction. It causes the reduction of something else, and this is what's being reduced. Similarly, we can say that this is an oxidizing agent because that will cause the carbon to become oxidized as it passes on its oxygen. So as this loses oxygen, that encourages the loss of oxygen, so that's a reducing agent. This is the oxidizing agent. An oxidizing agent is reduced, reducing agent is oxidized. Okay, hope that's clear. So this kind of thing can happen. This would happen on an industrial scale, and that would be something that takes place in a blast furnace. Finally, displacement reactions. Now, we've looked at displacement reactions. We've looked at the reactivity series of metals, and this is something I tested you on fairly recently. But we can also have displacement reactions with halogens as well. So here we have chlorine. The chlorine will displace the bromine from potassium bromide, so the bromine comes out and the chlorine replaces the bromide, so you form potassium chloride. Okay, so the chlorine becomes chloride, the bromide becomes bromine, and if you mix the potassium bromide in an aqueous solution, if you bubble that through with chlorine gas, you actually see a color change because potassium bromide over here is colorless, and the bromine gives an orange tinge, an orange colour if it is present. So that can actually be used very quickly, very visually, to confirm that indeed this chlorine gas, which is kind of like yellow greenish colour, it's a very faint colour, although it's a very faint colour, that chlorine gas will actually displace the bromine from the potassium bromide. So potassium bromide becomes bromine and potassium chloride in the presence of chlorine. And you can use that to show periodic trends in reactivity of the elements. So if you did this for over several experiments and you had bromides, chlorides and iodides, you would find that that chlorine would actually be at the top. It's the most reactive. It can displace bromine and iodine from its halogens, from those halide salts, and then you could have bromine, which is not high in reactivity not higher in reactivity compared to the chlorides. So bromine would actually not be able to displace chlorine from a chloride, but bromine can actually displace iodides. And then finally, the iodides are unreactive compared to bromine and chlorine. So if you have iodine in the presence of potassium bromide, for example, iodine will not undergo a displacement because iodine is the least reactive of the group 7 elements. So you can use displacement reactions for the group 7s. Right, okay, so I think that's time now to review and just think about some of the answers behind these questions. What type of reaction is this? I'll just pause the video and have a think. Okay, so this type of reaction looks as if it is an oxidation because this copper is gaining oxygen to form copper oxide. Now, you may have said combustion, but in actual fact, you wouldn't find that the copper burns. It's not the same. Combustion only really happens when you have a fuel or a material that easily burns. Right, question number 2, describe the results of 2 chemical tests of water. So basically, with the chemical test of water, I forgot to mention this, with the 2 chemical tests of water, the 2 chemical tests were actually covered in a quiz during our distance learning, and one way of testing it is by using anhydrous copper sulfate, which is white, And if you add if you add water to it, it releases a lot of heat, energy to surroundings. So the surroundings get warmer as the chemical energy, the store of chemical energy, transfers that heat energy to warm the surroundings, and you actually find that the anhydrous copper sulfate, which was white, turns blue. And the other way is by using anhydrous cobalt chloride. So anhydrous cobalt chloride, when you add water, that paper turns from blue to pink. So that's the answer to these two questions. That's the answer to this question. Describe the result of 2 chemical tests for water. Right, let's have a look at the third one. Thermal decomposition is a type of reaction in which only one chemical is written on the left. Explain why. Pause the video. So thermal decomposition is because it only has one chemical on the left-hand side, because the chemical actually breaks down into different chemicals itself. So here's the example: copper carbonate. Let's go to question number 4. Explain what you would expect to see if copper was placed into magnesium sulfate. Pause the video. So you should know that magnesium is higher in the reactivity series than copper, so absolutely nothing would be seen because the copper is not reactive enough to displace the sulfate from magnesium sulfate. So you won't get copper sulfate, you would just see copper in magnesium sulfate, no colour change, no chemical reaction takes place. And let's think about the 5th question. Displacement reactions can also be oxidation and reduction. Use examples of reactions to show this. Pause the video. Well, a good example was the blast furnace. So you can actually have a displacement reaction. You could say that carbon is higher in the reactivity series than iron, so it will displace the oxygen from iron oxide. So that's the product. But you can also say that this is also a redox reaction, because this is reduced, that's oxidized, that's the reducing agent, that's the oxidizing agent. Okay? So finally, just double check you know the answer to number 2. Describe the results of 2 chemical tests for water. Pause the video. Okay, so when you're giving 2 chemical tests for water, make sure that you give the right name. So it's anhydrous copper sulfate and anhydrous cobalt chloride. And then make sure that you're giving the proper colour changes. So anhydrous copper sulfate turns from white to blue, and anhydrous cobalt 2 chloride turns from blue to pink. Okay, there we go, and that's confirmation. Right, so thank you very much for that. Whizzed past the 2 chemical tests for water because I wanted to spend more time on reduction. I know that that was a weakness that we had in the classes when we were doing our distance learning as well, and when we were actually studying the blast furnace before. So I hope spending a little extra time on the on those topics has helped. The good news is that you seem to be okay with the anhydrous copper sulfate and the anhydrous cobalt chloride, but just make sure that you know what those 2 tests are. You can fully expect them to have a good chance of appearing in your assessment. Take care, stay safe, and I think we've got 3 more videos to do. So best of luck with your revision. Okay, bye for now.